Hello, this is Saad Bella, professor in electrical engineering at Msila University. I'm glad presenting the content video of waves and vibration lab classes. This video is supervised by TIC training team of Qusnطينة University. Why are lab experiments of waves and vibration so important? While learning about waves and vibration in theory is important, actually doing experiments helps us truly understand how they work. By conducting these labs, you'll not only deepen your understanding of the subject, but also develop valuable skills like observation, analysis, and problem solving. Plus, practical work also helps us connect theory to real-world applications. In fact, a question comes to mind: how many of labs should we do in this module during a season? This module contains different experiments, and usually we do just 4 to 5 lab classes. Amongst them we mention standing waves, resonance in series LC circuit, coupled pendulum, and simple harmonic motion in spring mass system. In our video, we're gonna just present a summary about 2 lab classes, which are resonance in series LC circuit and simple harmonic motion in spring mass system. Prior knowledge: students should have been studied Math 1, 2, and Physics. In addition to that, in the first lab class, which is resonance in series LC circuit, we need some necessary knowledge and background about electricity like Ohm's law. Also, the student should differentiate between AC and DC currents and their behavior, and the behavior of the set of components in each type of currents. In the second lab class, which is simple harmonic motion in spring mass system, it's based on energy conservation principle. In this case, mechanical energy is kept constant during conducting the experiment. Now, we start by showing each lab class. Let's start with resonance in series LC circuit. As it's shown in figure, the circuit contains a resistor, inductor, and capacitor. All are connected in series with an AC power supply and oscilloscope, like it's shown in the figure. By means of oscilloscope, we visualize the AC source voltage and the current passing through the resistor. To do so, for the source voltage, we connect just the probe between source ends. Concerning the current, it's achieved by watching the voltage across the resistor because it represents the image of the current, like indicated by using Ohm's law. Simply, resonance. What's resonance? This phenomenon occurs when the circuit natural frequency matches the frequency of the applied AC voltage, like it's shown in the figure. How to get it? We'll vary the frequency of the AC supply, and by using oscilloscope we observe the current in the circuit. At resonance, the resistor voltage and the current through it becomes in phase. This is like there is no inductance, no capacitor. Actually, it acts like it's purely resistive, like it's appeared in the figure. The right side, we remark that at resonance, the effect of L inductance conceals the effect of C because they have the same value of impedance but in opposite direction. Also, the current reaches its maximum value, like it's appeared in the figure. What students will be doing? Amongst what will students do in the lab? Students are supposed to fill up table by changing frequencies of voltage provided by the power supply, while noting the value of the current corresponding each point of indicated frequency, including resonance frequency. Students, they're gonna sketch current inflection of frequency, and the curve that's gotten is similar to this. What students will get by doing this lab as conclusion for this lab class: first, in resonance frequency, the delivered power from the voltage supply to the resistor is maximal, i.e. we'll find the current at its max, like it's shown in the figure. Secondly, the resistor voltage and current across it are in phase, and so there is no angle shift. The angle shift is 0. This is what students should be learned. Now let's talk about second lab class, which is simple harmonic motion in spring mass system. A spring mass system consists of a block attached to free end of spring. When pulling it by X, the spring expands and then comes back to its original position. In the absence of friction, this spring continues oscillating forever. This motion is called simple harmonic motion. Like it's shown in the figure, the spring is swinging around the original point. Right now, let's talk about the motion of this mouse. We can't fully describe it using energy. Why? Because the total energy of the system stays the same. At any point its movement, the mass has two types of energy, like it's shown in the figure: potential energy stored in the spring and kinetic energy due to its motion. Together, these energies make up the total mechanical energy of the system, like it's shown in the equation. Now, let's see the simulation using one of the free websites of simulation. Online, we say. When no friction, the spring will continue swing forever and the energy kept constant. This is what we call it the principle of energy conservation. At the end, like always, I'd like to thank each trainer of TIC program team of Constantine University. Thanks. See you again, inshallah.